Okay, so we're back. All right, so last time we also reminded us about discrete event system simulations and sort of how this simulation framework, the kind of salient features of the simulation framework and how they're used. I just want to take a quick time to highlight this nice article on simulated worlds that was from ORMS, which is kind of ORMS Today is the kind of Operations Research Management Science journal / magazine. It's kind of a professional magazine. And so this was back in October of 2015, so not too long ago, but sorry, this should say see Canvas for more details, so I can make sure that's posted up there. And in simulated worlds, they were drawing attention to the value of using simulation for operations research and industrial engineering. And so they mentioned specifically, called out discrete event system simulation models that are particularly well suited for things like parts in a manufacturing system, patients, vehicles, manufacturing, healthcare, logistics, transportation, military operations. So their point here is that most of the big problems for which operations researchers and industrial engineers are called into tend to take a shape that is very often amenable to these discrete event simulation models. And so these DES methods that we're learning how to do should be very portable to a wide range of applications and should be very valuable. This article is also nice in that if you read through it, it links to a large survey of a wide variety of DES simulation packages. They have a sort of a particular focus of FlexSim, but you can check out the survey and it kind of introduces a wide variety of others and kind of does some nice comparisons. So here's a visualization, I think from FlexSim. So this is an example of the type of sim. So this is a simulation of an airport, but they've rendered the simulation results so you can actually watch the entities walking around as these like 3D passengers. And then they stylized it so they've actually got these kind of like real-time stats that are on the sort of ground that these passengers are walking around on. So that's, I guess, part of the allure of these professional discrete event system simulation tools is that not only do they get the simulation job done, but they can package the results in kind of a cute way that can be very appealing to many different audiences. All right. So, so a question is, what other useful simulation frameworks do we have or can we use other than DES? Given the DES is so popular, but still we should be at least aware of some of the other ones. And so we live on a modeling continuum here. We're going to kind of live here, but I'm going to shift up and focus a little bit on system dynamics modeling. So system dynamics modeling is which there will be some slides in Lab 3 for that have a little bit more details about causal loop diagrams and some other things that you end up doing with system dynamics modeling. But this is the subject of IEE477, which is a required course for engineering management students and an optional course for industrial engineers. And in this simulation methodology, the focus really is around these things called stocks and flows. And so you can think of a stock as like a bucket of water and a flow as a valve which regulates the rate of water into that bucket. And that's why this is kind of a valve symbol here. And so you end up drawing a bunch of these stocks and flows that the value of certain stocks end up affecting the value of other flows, and that's what ends up creating the interdependencies between these stocks, and then you hit run and see how things go. And behind the scenes, every one of these stocks and flows is actually implemented like a little differential equation. And so when you're actually running these things, what you're doing is numerically integrating a little calculus problem. And so the state variables here, the stocks, those are the state variables in this case, they are changing smoothly over continuous time. So that's very different than the DES that we've been talking about, where you have the state only changing at discrete instants of time. So here, they're kind of constantly smoothly changing, the same way that water flowing into a bucket would cause that water level to smoothly change up and down. So what sort of things can you simulate with the system dynamics model? Well, one of the things you almost do in any system dynamics modeling course is you do this so-called susceptible, infected, recovered, or SIR model, because this is a standard analytical model that is used in mathematics, but you can easily build it inside one of these tools as well, because this is just, these are all derivatives, ds dt, di dt, and dr dt, and these are like the state variables and how they change. So this is a state variable s, I, and r, and then the dots mean this is how the state variable changes, and so the flows are these things over here. So you can see, like I was saying, that analytically, like when you write this thing out, this is saying that this flow, how s changes, depends on the current value of s and the current value of I. So the current state of the world changes how the state is changing. So the s is going to decrease by a value which is proportional to the value of s times the value of I. That's what this is just saying right here. And we can write all this out and do it all mathematically, or, so I'll just go over a stock is the state variable here, and a flow is the function that affects the rate of change. So those are the two big things in an SDM: is a stock, that's the state variable, and the flow. And instead of writing it that way, we can go into a program like VinSim, for example. That's what I think I drew this in. And you can draw the equivalent model, but we draw it in this way. So now we have a susceptible stock, an infected stock, and a recovered stock. And these arrows connecting them show that as this stock changes, as this stock decreases, this stock will increase at the same rate. So that's why these flows are connected. And as this stock decreases, this stock will increase at the same rate. And these little lines tell us how these rates end up being determined by other parameters. And so the infected population, that affects the total contact rate, and the total contact rate affects the infection rate. And so does this other parameter, infectivity, affect the infection rate. So all of those things go together, and you end up modulating how quickly those turn from susceptibles into infecteds. And so what people do when they analyze these models, I mean, they run them and see what happens, but you can also analyze them by looking for these feedback loops. So notice I've got a plus, and then this is implicitly a plus. And so this here looks like a positive feedback loop, whereas over here, this infected population's got a plus, but because I'm moving backwards down the flow, this is implicitly a negative. And so this is a negative feedback loop. So as you get more infecteds, you increase the infection rate, which brings you more infecteds. That's what I mean by positive feedback. Whereas here, as you increase the infecteds, that's going to actually increase the recovery rate, which will decrease the infecteds. And so this is your negative feedback loop. Whenever you have a positive feedback loop followed by a negative feedback loop, you typically have S-shaped growth. And so these are all the patterns that you learn to look for when you build these system dynamics models and these kind of graphical approaches, but then you can hit run and see what they look like, and it gives you these nice trajectories over time, but they're smooth trajectories. They are not the type of jagged trajectories that we'd see in a discrete event system simulation model. Now, programs like NetLogo also have some rudimentary system dynamics modeling tools built into them. So this is NetLogo's SDM tool. There are tons of SDM tools, just like there are tons of discrete event system simulation tools out there. So, but this is an example of a NetLogo stock and a flow, so maybe the symbology is just a little bit different, but I think you can kind of get the impression that you can put together these things, and if you understand the basic idea, then even though maybe some of the symbols might be a little different, you see these networks and you can look for the same sort of positive and negative feedbacks, and you can run them and analyze them. So this is a way to effectively build differential equation models of systems without actually having to write the differential equations. All right, Well, I'm going to pause right there, so go back and answer a couple of questions about the system dynamics modeling, and then we'll move on to the ABM stuff.